Today we start chapter 3. I think you'll like it. I say this every time, don't I? 3.1 is Scatterplots and Correlation. You guys know about scatterplots already? Some? Kind of. First, we're going to talk today about explanatory and response variables. What is an explanatory variable? Explanatory variables? It explains like your results, and we'll look at some examples in a minute. But you're already familiar with this one. We're going to construct scatterplots to display relationships. Once we get into it, I'm pretty sure you guys know how to do a scatterplot. Today, my emphasis was going to be on interpreting scatterplots. We've got the data, we make our graph, how do we interpret it? We'll measure linear association using correlation and interpret correlation. We'll see if we have time to get there. Kind of see how things go. So first things first, a response variable. It measures an outcome of a study. We know it, but let's write it again. Measures an outcome of a study. And your explanatory variable helps explain or influence changes in the response. Helps explain or influence changes in the response. So we had talked about this one. This is the first example I tried to teach you explanatory response with. We have how much it rains is going to determine like your weed growth or how much the grass grows, right? The amount of rain is your explanatory. It determines your response, which is your weed growth. How about this one? If we have the winning percentage of a basketball team, the more they win, we could expect to see the attendance at games to increase, right? The more they win, the greater the attendance. Could that also be flip-flopped? If you have a larger crowd, wouldn't the winning percentage maybe increase too? Maybe. You got a lot of people there rooting you on, you get super excited and pumped up, and then you play a little bit harder. So it could potentially go both ways. So sometimes we don't have a clear explanatory and response variable. And we also maybe talk about this one. This is just an additional example. If you don't quite understand, you could jot it down. Amount of daily exercise, so how much you exercise, your physical activity, could help explain your response, like your resting pulse rate. Explanatory and response. How about this one? Weight and height. Julie wants to know if she can predict a student's weight from his or her height. Information about height is easier to obtain than information about weight. Jim wants to know if there's a relationship between height and weight. So for each student, identify the explanatory and response variable if possible. If we talk about Julie, what is she saying the explanatory variable is and what she's saying the response is? She wants to know if she can predict a student's weight from his or her height. What's explanatory and what's response? The height's the explanatory, the weight would be the response. The explanatory would be the student height. The weight would be like the response. Because do you want to just go up to people and say, hey, how much do you weigh? Especially girls, right? So instead, we would maybe say, if we look at a set of data, we could look at students' heights and maybe from there kind of predict approximately what their weight would be. So displaying relationships with scatterplots. Scatterplots, here's kind of where we've come. We've looked at categorical data, and what kind of graphs use categorical data? We have bar graphs and pie charts. Pie charts, bar graphs, and pie charts, you get your categorical data in there, where we talk about our categories. What's the percent of people that have brown eyes, blue eyes, and so on? We can do that with bar graphs and pie charts. And then we talked about our histograms, our stem and leaf plots, our dot plots. Those are just one set of quantitative data, right? You just have every student's age, and you can make a graph there. Today, we build on this, and we have a scatter plot. It's taking two quantitative variables, and we're comparing that. So scatter plot, what's it do? It's the relationship between two quantitative variables. relationship between two quantitative variables. It's a scatter plot. And I know it says it on the next line, but if you write it, I'm a firm believer that you'll learn it. So maybe you have a student's height, you have their weight, you take both of those numbers, and it turns into 1 point on the graph. So each point on the graph represents like one student, their height and their weight, maybe their shoe size and their age. Some of you on your projects that you're working on, you're like, hey, maybe we take the time people spend studying and compare it with their GPA. You've got two categorical variables for one student, right? That's what we're doing. So how to make a scatter plot? Decide which variable should go on each axis. Explanatory variable goes on the x-axis. That's a quick way to remember it. Explanatory goes on x, and then your response will go on the y. We label and scale the axes and then plot your points. Explanatory goes on the x. So here's an example from the textbook. We've got the weights of some students, and we've got how much weight is in their backpack. What are we going to put as our explanatory, and what are we going to put as our response? The body weight would be your explanatory, and then your pack weight is the response. The larger you are, hopefully, the more you can carry in your backpack. Where's it at? All right, here we go. 9th grade students at the Webb schools go on a backpacking trip each fall. Students are divided into hiking groups of size 8 by selecting names from a hat. Before leaving, students and their backpacks are weighed. Here are data from one hiking group in a recent year. Okay, we've got the students with their weights and how much is in their backpack. So can we plot our points? 120, and then we go up to 26. And you plot your point, right? 187, and then up to 30. $109 and 26. So here's our second objective. We just created a scatter plot. Can you do that? Yeah. Can we interpret a scatter plot? That's the next thing that we talk about. So when we talk about interpreting scatter plots, before we talked about our socks to describe a distribution. When we talk about a scatter plot to describe our distribution, we use something called, I have yet to come up with something creative, DOS. I like it. Dogs outside fear squirrels. Okay. D stands for direction. O stands for outliers. Good. F stands for form, and S stands for strength. And here's your options. When I say direction, is it positive or is it negative? Outliers, you can tell what outliers are. Form, when we talk about form, it's either going to be a linear relationship or it's going to be curved. What's linear? Straight line, curved is curved, right? Strength, sometimes it will be like fairly weak, or you might say moderately strong. We're going to use these two words to help us describe it. It's either really weak, it might be fairly weak, it might be moderately strong, or it might be like really strong, very strong, extremely strong. Right. So here's a little trick, and this gets to talking about correlation already, and I'm not going to go that far just yet, but if you take and you draw a circle around your points, that's going to help you kind of determine, is it a weak correlation, is it a strong correlation? Have you guys talked about correlation much? Are you familiar with the word? Maybe when I show you it'll make more sense. So when I look at this, here's what I would say. I'm going to talk about the strength first, just because that's what goes in my blank. There's a moderately strong, positive, linear relationship between body weight and pack weight. There's a moderately strong, positive, linear relationship between body weight and pack weight. So this moderately strong, kind of self-explanatory, this refers to our strength. The positive. As we go from left to right, it's increasing, so I say it's positive. This would be our direction. In linear, for the most part, they form a straight line. I could draw a line through there. So this would be my form. What am I forgetting? Outlier. Does there appear to be any outliers? No? Maybe not. Some people in their head, they may be thinking, well, maybe. So don't maybe necessarily tell me that is an outlier. You might say something like this, that's possibly considered an outlier. We might say the student, which student is this? They had a body weight of, the student with body weight of 187 pounds is carrying 30 pounds in the backpack. And may be considered an outlier. Bless you. So identify it. What point is that specifically? And then tell me it's possibly an outlier. It's not that far outside of our trends to say, no, that's not an outlier, but it could be. And then we can also, it asks you just kind of like in general, what do you notice? When I look at this, what tends to be the general pattern? If I talk about body weights, my lighter students carry the lighter backpacks and the heavier students carry the heavier backpacks, right? So just give me a short sentence, quick sentence. The lighter students. Yeah, or the lighter you weigh, the lighter your backpack. So just real quick, sometimes on the next page you'll hear things referred to as positive associations and negative associations. I'd say this is positive association. The direction is positive. And what happens is X increases, our Y's are increasing as well. So positive association, we could say as X increases, Y also increases. As X increases, Y also increases. What if I had a scatter plot over here that looked like this? It'd be a negative association, and so we would say, as X increases, what happens to our Y values? They're decreasing. As X increases, Y decreases. So that would be a negative association. Sweet? How about here? And then we'll take a little break. Looking at this scatter plot, what would you say about the strength? Is that strong, weak? Moderately strong? We're going to say this one's moderately strong. We'll get to some in a little bit that are moderately weak. So there is a moderately strong. What direction is it going? Positive or negative? Negative. There's a moderately strong, negative, curved. This one is distinctly curved, without a doubt, right? We look at this and I circle my dots, and without a doubt, that is curved. Moderately strong, negative, curved relationship between the percent of students in the state who take the ACT and the mean SAT math score. And notice what they say in this next bullet here. They say that there are two distinct clusters of states and two possible outliers that fall outside the overall pattern. So they're talking to us about these two outliers, and you see that there's kind of two separate clusters of data there? Yeah? So that's just a little tidbit. Check this out. This was one student's final project. They went through, they surveyed 60 students, they found students' GPA, and they also found ACT scores for students from Northwest, Springport, and I believe they said Napoleon was the third school. They found this information. Would you say this is curved, or would you say that's linear? So it's kind of tricky, isn't it? Because if you look at it, you're like, oh, that appears to be curved, right? But then you're like, well, if I forget this point and I forget this point, then what do we have? It's really pretty linear, right? So if you forget about those 2 points, so really what you have to do is you need to look at the data as a whole. Don't worry about like these extra 2 points out here. What overall is the data tending to do? It tends to be really fairly linear. So if you say it's fairly linear, or if you say it's slightly curved, you can use words in there that say slightly or moderately, just so that we're not, that's definitely a curved relationship. Use words that help support your answers. Like, it's slightly curved. Yeah, you'd be right on that. All right, grab your notes. Let's keep going. Linear relationships are important because a straight line is a simple pattern that is quite common, right? Linear lines, they're straight lines, quite common. We see them a lot. Unfortunately, our eyes are not good judges of how strong a linear relationship is. So here's where we calculate correlation. And we're probably not going to get into calculating it today, but we're just going to estimate today. Correlation, R, is a measure of the strength. It's a measure of the strength of the linear relationship between two quantitative variables. Measure of the strength of the linear relationship between two quantitative variables. Correlation is always a number less than or equal to positive 1 and greater than or equal to negative 1. R is between negative 1 and 1. Let me say that. If R is greater than 1, we say this is a positive association. If R is positive, it's a positive association. If R is less than 0, it's a negative association. If it's near 0, that means it's very weak. The strength increases as we approach negative 1 or positive 1. And if R equals exactly negative 1, or if R equals exactly positive 1, that's a perfect linear relationship, which is very rare that every point would lie on the exact same line. But if R is exactly negative 1 or positive 1, it's a perfect linear relationship. So, if you turn the page, you'll see these graphs. And already, here's the estimates of the correlation. If I put a circle around all of these points, does it tend to go positive? Does it tend to go negative? It's just completely scattered. We have no idea, so we would say the correlation is 0. It's very weak. Do you see it? I look at this one. I put a circle around this one to incorporate all those points, and it tends to be, my circle tends to be a little bit more negative, so it's like negative 0.3. It's still pretty close to 0. The larger the circle, it's more like a 0, so you can kind of remember 0 is weak, and it's all scattered like that. We circle around this one. We get positive, and 0.5, it's a little stronger. Halfway in between 0 and 1. We look at this one. This one's even stronger than the last one. It's negative, and you have negative 0.7. Do you see what I'm doing? How about here? We circle this one. It's a lot skinnier. It's if you think about it, it's more like the shape of a 1 if you think about putting a 1 in here. And we circle this one. It's definitely negative. Not every point is on the line, but it's pretty close, so that's where we say negative 0.99, just as a rough estimate. Yeah? How about here? How to calculate correlation. Here's the formula for it. You want to do it by hand? No. It's complicated, right? I would never expect you to do this by hand, and even for the AP test, you would not have to do that by hand. Okay? The calculator does it for you. Here's my question. Do we know what all these different variables and symbols stand for? What is R? Correlation? What is N? Your number or your count? Yep. How many pieces of data we have? How many individuals? What does this symbol mean? The summation? Or sum? We haven't talked about that one a ton in here. What would x2 and y2? It's like x2 and y2 from a certain point. It's like the second point in our data, your x and your y values. X bar? Average of the x's? What's y bar? Average of the y's? S sub x? Yeah, standard deviation of your x's. And this one, S sub y? Standard deviation of the y's. Look at all you guys have learned this year. Fun stuff. Correlation makes no distinction between explanatory and response variables. R does not change when we change the units of measurement on X or Y or both. If we had our heights and we say, hey, let's convert these into inches now, and we recalculate the scale, the correlation is still going to be exactly the same when we change the units. Okay? The data still stays the same, except we just change the units. But R does not change. Correlation R itself has no unit of measurement. So we don't say R equals 0.5 centimeters. We just say R equals 0.5 or R equals 0.1 or whatever. Correlation requires that both variables be quantitative. Scatterplots deal only with quantitative data. Correlation does not describe curved relationships. We see a scatter plot, it's curved. Don't tell me R equals something. You'll never have an R if the data is curved. And I would say even put a star by that. Do not do that. Correlation is not resistant. It is strongly affected by a few outlying observations, and we'll play with that a little bit tomorrow with the calculators. And correlation is not a complete summary. Not a complete summary of two variable data. You can't just tell me the correlation is this, it's relatively strong. I need to know about the outliers, I need to know about the form and the direction and all that. When we look here, what would you estimate that correlation to be? 0.9, 0.8? Yeah, any of those would be legit responses. Yeah, so make note of that on your paper. It's positive, it's increasing. If you put a circle around there, it's pretty strong. How about this one? .2, 0.3, yeah, it's positive, it's increasing, right? If I were to put a line through here, we draw it this direction. No, it's not going to come close to hitting many of those, but it's positive. How about that one? 0. Yeah, it's like, does my line go positive? Does it go negative? I don't even know. I'd probably say 0 on that one. If some of you said negative 0.1 or positive 0.1, I'd accept that as long as we're in like this same relative ballpark here. And this one? Negative 0.05. Could, yep. Negative 0.1. Yeah, somewhere around there. Because again, you put a circle around all these dots, it's really wide, really scattered. And we're going to hold off there for today.